Welcome back to our journey into AI. Now, last time we got machines to sort things into nice, neat categories, but today we are seriously leveling up. We're going to stop asking which one and start asking a much, much more powerful question. How much? Welcome to the world of regression. Let's get into it. So up until now, everything we've talked about has been about labels. Is this email spam or not spam? Is this picture a cat or a dog? But what happens when the answer isn't a simple category? What if it's a specific number? Well, that's the jump we're making today, from classification right into regression. Okay, let's really see the difference here. On one side, you've got classification. It's all about sorting things into these predefined buckets. But on the other side, you've got regression, and that's all about pinpointing a very specific value on a spectrum. Think of it like this. Classification asks, is this house in a good neighborhood? But regression asks, what is the exact price of this house? See the difference? So really, anytime you're trying to predict a specific amount of something, you're now playing in the world of regression. And when you think about it, it's everywhere. Predicting the future price of a stock, forecasting the box office revenue for a new blockbuster movie, or even a self-driving car figuring out the precise distance to an obstacle. All of these need a specific number, and that is exactly what regression is built to do. To really get a handle on how this works, let's use an analogy that I'm sure you know inside and out: your grocery bill. Seriously. This super common everyday calculation, it's a perfect model for the most basic but also one of the most powerful types of regression: linear regression. And this quote right here, it gets right to the heart of it. A linear model is basically just assuming that the final result is just the sum of the influences of all its different pieces. Kind of like, you guessed it, your shopping bill. Let's break this down. The amount of each item, 2.5 kilos of potatoes, 1 kilo of carrots, 2 bottles of milk, those are our inputs. In machine learning lingo, we call these features. The model takes each feature, multiplies it by its price, and then just adds it all up to get the final prediction: 15 euros. Simple, right? That is the core logic of linear regression in a nutshell. Now, in the machine learning world, we don't call these prices prices. We have a fancier name: coefficients, or sometimes weights. So the weight for potatoes is 2, the weight for carrots is 4, and so on. A higher weight just means that feature has a bigger say in the final outcome. So the whole process of training a model is really just the machine's quest to find the absolute perfect set of weights. But hang on, what's our starting point? Before we add anything to our shopping cart, the total is just 0. But in more complex models, we need a different kind of starting point. We call this the intercept. Let's actually switch analogies for a second. Imagine we're predicting life expectancy. We might start with a baseline for a non-smoking woman, let's say 80 years. That's our intercept. From there, we adjust that number up or down based on all the other features, like diet or exercise. Okay, so the shopping analogy is great for getting the math, but what does a regression model actually look like when it's doing its thing? How does it take all this raw data and turn it into a tool that can actually make predictions? Let's go from a simple calculation to seeing the big picture. Okay, imagine we've got this totally made-up data from some tech company. Every single dot is a programmer, and we're plotting how many cups of coffee they drink versus how many lines of code they write. Just looking at it, you can already see a pattern with your own eyes, right? It kind of looks like more coffee equals more code. But how do we make that relationship precise? And this is what the linear regression model does. It looks at all those scattered points, and it finds the one single straight line that best slices through all of them. It's the line that minimizes the average distance to every single point. This line is the pattern. It has captured the very essence of the relationship between coffee and code. So you have to understand, that line is the model. It's learned the pattern from the data. And now the magic can happen. If a brand new programmer joins the team, and let's say she drinks 3.5 cups of coffee a day, we don't have to guess anymore. We just find her spot on the coffee axis, go straight up to our line, and bam, we have our prediction for how many lines of code she'll write. We've just turned a bunch of scattered data points into a predictive machine. So we've built this amazing tool for predicting numbers. But this leads to a really interesting thought. What if we wanted to go back to our old problem of predicting a label? A simple yes or no. Is there any way we could adapt this number predicting machine to do that for us? Let's think about that for a second. We've got a system that spits out a continuous number, and we need a system that spits out a simple category. How on earth could we possibly bridge that gap? Well, it turns out we absolutely can. The solution is this brilliantly simple yet incredibly powerful technique called logistic regression. You can think of it as a clever little hack that lets us use the number crunching power of linear regression to solve a classification problem. Here's how it works. It's so cool. First, we use our linear model just like we did before to calculate a number. But then we add one incredibly simple rule. We just look at the sign of the results. If the number is positive, we predict yes. If it's negative, we predict no. That's it. We just took a regression output and turned it into a classification decision. All right, let's pull back for a moment and look at the big picture. We've seen how linear regression can predict numbers, and we've seen how logistic regression can predict simple labels. This combo makes regression one of the true workhorses of machine learning. And you'll find these regression models working behind the scenes literally everywhere, predicting house prices, forecasting how much money a movie will make, managing inventory in a store, setting insurance premiums. These are all huge, complex, real-world problems being solved every single day with regression. It is an absolute cornerstone of modern data science. Because at the end of the day, this is what it's all about. It doesn't matter if we're classifying or regressing or using some other technique we haven't even talked about yet. The fundamental goal is always the same: to find meaningful patterns in data that we can use to make smarter predictions about the future. And this brings us to such a critical point about machine learning in general. There's no magic bullet. There is no one algorithm to rule them all. Choosing the right tool for the job is everything. Sometimes you need a classifier, other times you need a regression model. Knowing which one to use and when is what separates powerful data science from just, making a guess. But our line drawing model, it does have a weakness. It assumes the relationship between things is, linear, that it's a straight line. So what happens when the real world is messy and more complex? What do we do when the patterns in our data are curved and twisted and complicated? What's the next tool we need in our toolkit for that? Well, we're going to tackle that very question in our next session.